Right. So here, this is the next question. This is about Gram-Schmidt orthogonalization process. What is this Gram-Schmidt orthogonalization process? For example, they have given a set of linearly independent vectors, a set of linearly independent vectors. Okay, so we can call it as basis states. Now we want to convert this set of linearly independent vectors. That means this process will convert them into complete basis. Complete basis. What is the meaning of basis and complete? What is the difference between basis and complete basis? So here the basis, complete basis means they obey or satisfy orthonormal condition. Orthonormal condition. Okay, that means these basis states need not to satisfy this condition. So if you apply this process, whatever the basis states we are getting from this process, they definitely satisfy the orthonormal condition. That is, if you have the inner product psi I, psi j, if you make the inner product of two vectors, we'll get delta ij, canonical delta, which is equal to either 1 or 0. 1 if I equal to j, 0 if I is not equal to j. Earlier problems we have already discussed. 1 means normalization condition, that 0 is the orthogonal condition. Okay, so now let us suppose we have a set of vectors, let us say v1 and v2 and v3. Let us suppose these are a given set of linearly independent vectors. These are basis states. So now we want to convert them into a complete basis. Let us suppose the corresponding complete basis states are E1 cap and E2 cap and E3 cap, so on. So let us discuss how to construct. So for the first one, E1, you have to take this first vector as it is. That means let us suppose U1 equal to V1. First I will get U1, and from this I will write the corresponding unit vector, that is simply a vector by its magnitude. So we can write this as u1 by its a normalization constant, which is nothing but norm, or we can write it as inner product. Right. So we got the first vector, this one. This is very easy. And next, if you want to get the second one, so here onwards the process starts. Listen carefully. First one is a straightforward. Okay. Next. So here you have to find u2 next. How to get u2? So u2 equal to, it is defined as v2, the given vector, second vector, minus projection of v2 over u1. What is the meaning of this? So we have to find the projection of v2 over u1. For this, we have to take the projection operator corresponding to u1. What is the projection operator corresponding to u1? Already you got this unit vector. So just to take the projection operator, e1 cap, e2 cap. This is the projection operator corresponding to u1. So just take this and operate on v2, which is finally u2 equal to v2 minus, so one more time, projection of v2 over u1. That means take the projection operator corresponding to u1, e1 operates on v2. No need to get tension. Here you will get a scalar, and that scalar is multiplied with this e1, and you have to just subtract that from v2, second one. So as usual, I have to find the corresponding unit vector, that is e2 cap. Just I am finding the unit vector corresponding to u2, which is u2 by its magnitude or norm, or we can say this is a simply under root normalization constant u2 u2. Earlier we have given that is 1 by under root mod a square plus mod b square, which is nothing but the inner product of a psi, the inner product of u2. And similarly, second, if you want to find this E3, first I have to find the corresponding U3. So U3 equal to, this is V3 minus, see carefully here already we got two things, U1 and U2. So that's why projection of V3 over U1 minus projection of V3 over U2. So let us write this. So same concept. What is the meaning of a projection of a V3 over U1? You just take the projection operator corresponding to U1 and operate on V3. So which is nothing but the projection operator corresponding to U1. This is outer product operates on V3 minus, this is a projection of V3 over U2. You just take the projection operator corresponding to U2, which is outer product E2 operates on V3. That's it. So once you got this U2, you can find the corresponding unit vector E3 equal to the vector by its magnitude or inner product or norm, whatever it is, U3 like this. So if you want to write more generally, so you can write like this also. Let me write here itself. Yeah, I will write here. So if you want to write more generally, so let us find u. This is so we have to find this uk from vk minus. Here is a summation. If you observe carefully, for v3 we got two terms here. So summation. I'm taking some other dummy weight index j. I'm taking the outer product ej. Okay. So it operates on vk. But if you observe carefully, whenever you are finding u3, you got only two terms here. One is corresponding to u1, another is the projection operator corresponding to u2. So you will get the projection operators. How many? Whenever you are finding u3, you got two projection operators. Whenever you are finding uk, this j is running from 1 to k minus 1. That's it. So this is once you got this uk, you can find the unit vector, corresponding unit vector uk by its magnitude. So this is the Gram-Schmidt orthogonalization process. Now let us consider one example for this and discuss. Okay. Now here I am taking one example to understand this method. So I have taken two vectors 3 1 and 2 2. If you see carefully, if you find the inner product of those two, it is not equal to 0. So it is not a complete basis. So how to make it a complete basis? Okay. So let us suppose this is our V1 and this is our V2. So first, as usual, I have to define U1, which is nothing but a V1, first vector as it is, no issue. So which is nothing but a 3 1. So directly we can find the unit vector corresponding to this V1, which is V1 by its normalization constant, which is nothing but 1 by under root a square plus b square. Earlier problems I have already discussed. This is 1 over under root 10 3 1. So that is the even cap. Next, we have to find this E2. But before going to find that, first we have to find U2. u2 equal to this v2 minus projection of v2 over u1. So earlier we have already discussed this one. So what is the meaning of projection of v2 over u1? You just take the projection operator corresponding to u1 and operate on v2. So here what is the projection operator corresponding to this v2 minus this projection operator e1, sorry, so e1 cap, this is the projection operator corresponding to this and which is operating on v2. And if you see carefully, here this is the inner product. Now let us find this v2, given v2 as it is, which is a 2 2 minus, and here we have this inner product. Let us write this matrix form. This is the ket vector, so that's why e1 cap, which is 1 over root 10, this is the ket vector as it is a column, and this is the bra vector, again 1 over root 10 whole square, and but this is a bra vector, that's why I have to write it as a row matrix, and this is a v2, the given one v2 as it is 2 2. Now we just find this product. This is a row and a column come from this side. So row and a column, 3 2s are 6 plus 1, 2, that is 8. So we can write this as a 2 2 minus, this is 1 by 10, and here we are getting this scalar. This scalar is nothing but 8. So this is 8 by 10 into 3 1. You just subtract these two, and here you will get minus 2 by 5 and 6 by 5. So this is your u2, and from this we have to find e2 cap. You just find this e2 cap yourself, and this e2 cap equal to u2 by under root this inner product. And I think this answer is equal to 1 over root 10. You'll get I think 1 minus 3, or sorry, minus 1 3. You just find it. Just take this same thing divided by this under root a square plus b square. Please do it yourself, and this is your final answer. Now you got e1 and e2 cap, so please check what is our result. So we got this complete basis like this: 1 over root 10 3 1, 1 over root 10 minus 1 3. If you find this inner product of these two, you are getting 0, that is orthogonal. And if you take the self inner product, you will get 1, so which satisfies orthonormal condition. So this method is basically, if a set of linearly independent vectors is given, we can convert them into complete basis which satisfies orthonormal condition, right? So here if you have any doubt, please contact. Okay, right. Go to the next one. So here they are asking to represent the Pauli operators uh, in the outer product notation. Okay, so let us start. So let me take this identity operator first. This is 1 0 0 1. Already basis states are given. If you observe carefully, this is the basis state. But how to write this outer product form? So whenever you want to write the outer product form, first write the matrix representation of this. So the matrix representation I told you already. So here you have to take a input basis. Here our input and output bases are same. So this is ket 0, ket 1, and this is a bra 0 and bra 1. So my matrix is nothing but here 1 0 0 1. So if you want to write the outer product form, it's very simple. Wherever you have 1, so please round up those things. That means you will get only those terms corresponding to 1. Okay. So here I round up this one. Then I can write this identity operator in the outer product form. It's very simple. You just see this. Corresponding to 1, here you have bra vector 0 and ket vector 0. So outer product means ket into bra. I repeat, outer product means ket into bra. Okay. So just make this bra vector as a ket vector and this ket vector as a bra vector, and whatever the coefficient you have, non-zero coefficient, non-zero term, this is a non-zero, whatever you have this coefficient, just take it and write here plus. And of course these terms won't get, so because of zeros, and here we have 1. Okay, so again this is nothing but make this bra vector as a ket vector and make this ket vector as a bra vector. Now let us go to this Pauli matrices. This is x 0 1 1 0. So first let me write this matrix representation: ket 0, ket 1, bra 0, bra 1. So 0 1 1 0. You need not to bother about that 0 elements, leave it, only just round up this 1 and this 1. Now see this one. So the Pauli X matrix X is equal to, here this is the 1, corresponding to this one, here is the bra vector, make it a ket vector. Of course this coefficient whatever you have, it will come here, and this is the corresponding ket vector, make it a bra vector. That's it. Plus, and here is a 1, make this I mean coefficient is 1, make this a bra as a ket, and the corresponding make this a ket as a bra. So similarly you can go with the y. This is a 0 minus iota and a 0. So first let us write this matrix representation: y ket 0, ket 1, bra 0, bra 1. So this is 0 minus iota, iota 0. So wherever non-zero is there, just round up. So here this is a y equal to the first element, non-zero element, minus iota. The corresponding to this is the bra vector and this is the ket vector. So just convert this bra as a ket and write this ket as a bra, plus next non-zero element iota and make this bra as a ket and the corresponding ket make it as a bra. That's it. So if you take this Z, so similarly you please try this. Z is equal to this 1 0 0 minus 1. I request you please try this. You will get this in the outer product form. Here is a 1, here is a minus 1. So you'll get minus 1 1 because it's a diagonal matrix. You please try this. And this is one way of writing operators in outer product form. Let us try in another way also. Whenever you have some operator, any operator can be written as a outer product form. That means a linear combination of outer products. Linear combination of outer products of basis states. Okay, so how can we write this? For example, you have this Pauli X matrix I am taking. So if X operates on 0, we are getting this 1, and X operates on 1, we get 0. So based on this operation, we can write the outer product form. So what is that outer product form? This outer product form is given by always a summation over I, always this is the initial state and this is the final state. So what, I'm sorry, I think, yeah, this is, here this is a psi initial and this is the psi final. This is the outer product form. If you observe carefully, X is equal to, now this is the initial state 0 and finally we got 1. So that's why we can write it as ket 0, bra 1, plus initial state 1 and a final state 0. And similarly, if you take this y, that means y operates on 0, what you will get a iota 1, and y operates on 1, you will get minus iota 0. Let us check the outer product form. The outer product form is equal to simply summation over I. Remember, psi initial is in the ket and psi final is in the bra vector. Okay, so careful. So now y is equal to, so what is the initial state here? Ket 0. What is the final state? Careful, you have to take this iota also, iota 1. But whenever there is a complex, there is a constant in the bra vector, you will get the complex conjugate. So that's why this is a minus iota. I'm sorry, let me finish it. Plus, next, what is this input here? Sorry, initial state here 1, and final state minus iota 0. You have to take this constant also. And we know already, whenever there is a constant inside the bra vector, you will get a complex conjugate minus iota 0, 1. And whenever there is a constant, say you will get a complex conjugate which is iota. So let us compare this with the earlier one. So minus iota 0, 1 outer product plus iota 1, 0 outer product. Yes, same thing. And third one, I request you please try. So whenever z operates on 0, this is based on the operations, and z operates on 1, we'll get just a small phase change, that is pi phase change minus 1. So I hope you please try this and you will get this same thing. That's it. So initial, final, initial and final, there is a minus sign, that's why you will get minus. So any operator, we can write this as a outer product form by using this technique, which is a summation over I outer product, but that outer product ket psi initial and bra psi final. Please remember, initial state is in the ket and final state is in the bra vector, right? Right. So here this is the next question, and here they are asking this outer product Vj in the basis of, we want to represent this in the basis of vi. Remember one thing, whenever you are changing the basis, always use a completeness rule. Okay, so one more time, completeness rule, completeness rule. So here they have given, they want to change into this basis, that's why we can write the completeness rule, this I equal to summation over I, this outer product, the sum of all outer products of the basis states is always equal to this identity operator. Okay, now let's come back to our problem. So here they have given this outer product operator, that is Vj, Vj. Okay, so now we can write this as I Vj, right? Now I'm going to replace this I with this completeness rule, which is summation over I. This is the outer product Vi, and the rest of the things as it is. Just write this as it is. Don't get tension, as it is. Now, if you observe carefully, so here we have one inner product. So in the earlier problems also we discussed, this inner product is nothing but Kronecker delta, delta ij. So we can write this as summation over I, and this is delta ij. Okay, and here we have again one more outer product we got. This is a Vi, careful, and the rest of this the remaining thing is a Vj. So here we have written this Vj outer product in this form. So what is the meaning of this? So finally, one more time I'm writing here. So Vj equal to, I got this summation over j, sorry, summation over I, delta ij, and this outer product vi vj. Okay. So you know this property of Kronecker delta. This is equal to 1 only when I equal to j, that is a diagonal, and 0 if I is not equal to j. Okay. So if I take this matrix representation like this, now let us suppose this is the outer product, given outer product, and here I am taking the basis states input. So ket vectors v1, v2, and v3, so on, so on. Let us say somewhere vj or vi, anything you can take. It's not a problem. So vi or vj, because only I equal to j, then only it is 1. So here bra vector v1 and v2 and so on. Okay, v3 and so on. This is a vj. So where you will get 1? Oh, sorry, not along the diagonals. Where you will get this 1 minute. Right, okay. So this means what? Here we will get only one element and the rest of the elements are 0. So we remain with either vi outer product or vj anything, because all the terms will be 0 except this I equal to j. So that's why just I am taking this vj here. So only this term remains and the rest of the terms are 0. So here Vj and here Vj. So only this one is a 1 and the rest of the elements are a 0. So that's it. So if you want some more clarity, so this is having a best example. So here, for example, if you want to write this 0 0, which is nothing but 1 0 0 0. This is the matrix representation. So only the element corresponding to ket 0 and bra 0 is 1, rest of the elements are 0. And similarly, if you take this outer product 1 1, so this is 0 0 0 1. So here the only this element corresponding to ket 1 and bra 1. So if you have any confusion here, so please see this example, you will get clarity. So only that element is 1 and the rest of the elements are 0. Okay, so that's it. And if you have any doubt, so please contact. Thank you.